Okay, so we will do these three calculations here. And like I said moments ago, that a titration calculation is essentially a stoichiometry problem, just like we did when we worked on the stoichiometry problems at the end of the solutions unit. And it's one of those stoichiometry problems that, as you can see at the end of the question, what was the concentration of the acetic acid? It's one of those questions where we're looking for the concentration, all right? You don't need to copy these because I have a sheet with all of this stuff on, all right? So you can just do the answers, and I'll get you that sheet. Now, again, like I said, this is one of those, yeah, if you didn't get the sheet, you don't have to copy these down. I can get you the sheet in a moment, where you've got to find the unknown concentration. So again, because it's stoichiometry, we do need a balanced chemical equation. We need to write all of our stuff underneath the balanced chemical equation so that we can make sense of what we're doing. Now, sometimes a question like this is mistaken as a dilution question. If you truly, don't have a good understanding, it's sometimes very easy to think that you've got a V1 and you've got a C1 and you've got a V2 and you want to find a C2. But if you read the question carefully, it says that the sodium hydroxide is titrated against acetic acid. There's two chemicals in that question. That kind of implies that there's a reaction going on. The equation C1V1 equals C2V2 is our dilution equation. And that equation is used when you have one chemical and you're adding more water to it to make it a diluted version of that solution. Now, I'll tell you right now, if you use the equation C1V1 equals C2V2, in this situation, for this question, you will get the correct answer. And the only reason that you do is because the mole ratio is 1 to 1. As soon as the mole ratio is not 1 to 1, the answer is incorrect. On a test, if you should be doing a stoichiometry calculation and you don't understand the question and you use the dilution equation, even though you get the correct answer, I'll give you 2 out of 5 because you recognized that there's volumes and concentrations, but you did not analyze the question correctly. And my job is to mark it based on how you answer the question. All right, that's why we want to see our work. So these are not dilution questions. We don't use C1V1 equals C2V2. We start with a balanced chemical equation. So let's go ahead and do that. So we're reacting some sodium hydroxide, NaOH, and we are neutralizing it against acetic acid. Acetic acid is that molecule that we've written in 2 different ways, CH3COOH, but there's also the other way of writing it. We can write it that way. The other way uses the acetate ion, which is on the back of your periodic table. Actually, let's do it that way. H, because it's an acid, and then on the back of your periodic table, the acetate is the C2H3O2. Is that what that is, I believe? Check it out for me. Make sure that that's the acetate ion. Did I get it right? Yep. And then with the H, it's acetic acid. And that's going to then do a double displacement neutralization reaction. This H is going to go with the OH, H2O. The sodium is going to go with the acetate, and you're going to have NaC2H3O2. And that's off on the end. I apologize, but it's not important. This is 1 to 1 to 1 to 1 because it's simply a single hydroxide with a single H that is being traded. Just like before, we'll write our information underneath. 23.45 milliliters. There's our volume. That's where we write our volume. Concentration, 0.275 moles per liter. The other volume, 10.00 milliliters. And the question asks, what is the concentration? Remember, the concentration is the conversion factor. So where it says, what is the concentration of the acetic acid? In where we put the conversion factor, I put C equals N over V. Moles over to moles with the mole ratio. Just as before, I've suggested when it asks for what is the concentration, you write down C equals N over V. We've already got it here, but let's make it a little bigger so we can actually put our numbers into it. And just as before, we will get our information. There's the V. It's going to go in there. Right here is the N. That's the moles we need. When we figure that out, we're going to put that in there. Put everything in the proper units, divide, and away you go. You've got it. We will be using stoichiometry to figure out those moles. We can get all the way over there. We put everything in. So let's go ahead. I need to have this in liters. 1, 2, 3, 0.0234 liters. The reason we know it to so many significant digits is because we used our burette, and our burette can read to the second decimal point. I'll talk more about that when we actually do an experiment. We also know this 10 milliliters, that came from the pipette, and we also know that to exactly 4 significant digits. Using the concentration, liters on the bottom, 1 liter, 0.275 moles on the top. Mole ratio, this one is 1 to 1. Again, that's the only reason why that dilution equation will get you a correct number, but it's not for the right reasons. Okay, so I'll take those numbers when they come in. I'll take the N, you got it? Anthony, what do you got? Let's have one more significant digit for the 3 here, because this is 3 and that's 4. -3, and that is moles. Doesn't have to be in scientific notation, but many of you are getting good at setting your calculator for scientific notation. I like scientific notation. It's easier to write. I got no problems with it. It's easier to round as well. Now we're ready to put that in the C equals N over V, and I'm going to be tight on space here. I'm going to have the N 6.45 times 10 to the -3. I apologize, the unit went off the end. The volume is 10 milliliters in liters. 1, 2, 3, 0.01000. Again, I apologize, the unit has fallen off the end. And I'm going to make some space here. I'm going to bring the answer down underneath here. And what do we get? Yep, Nick? 0.645 moles per liter, and that is correct to 3 significant digits. And that's what makes a titration such a powerful laboratory technique. It allows us to take a solution that we've standardized, that we know very precisely its concentration, and by using these precise volume measurements, we can find the concentration of an unknown solution to the same degree of precision, 3 significant digits. All right? Let's do another one. They're on the titration handout that I gave out yesterday. They're just the slides of the titration handout, so you don't need to copy them, and if you don't have one, I'll get you one in a moment. All right? I handed that out yesterday, right? Yep. Okay. It's the same problem. All of these things are the same. Balanced chemical equation, put your numbers underneath, figure out the N and get the V and away you go. This one's different in that I'm using barium hydroxide, BaOH2. So I'm going to put together one here that has a 2-to-1 ratio. Ooh, tricky stuff. This time it's reacting with nitric acid. And you guys hate the acids. What's the formula for nitric acid? Yep, Chantel? Yep, HNO3, based on the nitrate. HNO3. I see a trend. Chantel always gives me the acid answers. She's got it figured out. Any questions on how to figure that out? Ask Chantel. Again, it's a neutralization. This H is going to go with the OH, and it's going to make water. But you'll notice there's two of them, so I'm going to need something to balance it up. The barium is going to come with the nitrate. Barium is a +2 ion, so we need 2 of those nitrates. Remember, cross over to get the formulas, then balance. 2 nitrates, I've only got 1 there, so I need the 2 there. And now each one of these H's will get together with each one of these OH's to produce an OH, or a water, and so I'm going to get 2 of them. So we now have a 2-to-1 ratio. Put the numbers down, get your values, calculate it out. So it's the same type thing. 17.05 milliliters. I'm going to try to compact this into the space so I can fit it on the screen. 0.247 moles per liter. 10 milliliters. C equals N over V. Moles, mole ratio. There's the V, figure out the moles, put it in. Same thing. Again, I'll put my C equals N over V up here and make it a little smaller so I can make it fit. I'm going to use stoichiometry to find the moles of HNO3. Again, 3 significant digits on our concentration. That's going to be our limiting one there. For every 1 barium hydroxide on the bottom, I need 2 nitric acid molecules on the top. What I have on the bottom, what I want on the top. And Barbara has the answer. What do you have? 0.008, sorry? 42, and that's moles, and that's not scientific notation, which is okay. Doesn't have to be. And now I do the same calculation. 0.00842 moles divided by 0.01000 liters. And when you divide by 0.01, which is essentially dividing by 1/100th, it's the same as multiplying by 100. You're just moving the decimal the other way. This decimal is going to go 1, 2 into that position, 0.842 moles per liter. All right? If you didn't follow that last statement about moving the decimal place over, it's all right. As you continue on in science, someday you'll know what I'm talking about. Okay? Any questions or concerns on these? They're very straightforward. Now on the sheet, and as you can see here on the slide, this is where in the past I've done the demonstration titration, and I would have done 3 trials, and I would have put, my initial reading, 0.00. My final reading, what was it? I said the number. I don't even know where I wrote it down, 20.15 or something like that. Now, when you do your second trial, have all of your Erlenmeyer flasks in a row there all ready to go, you wouldn't reload. Your final becomes the next initial. and then you just titrate until it is done, and then you get its new final and you subtract. If we were dealing with a 20 milliliter approximately, I couldn't do a third one because a burette only holds 50 milliliters, so I'd have to reload at that point. But we don't reload unless we have to, okay? Now, I'm not going to do that particular demonstration. We saw the way a titration is done. You'll do that next week. Let's just finish with this last example. Now, I made a change here because there was an error. On yours, I believe the initial reading for the third one says 30. Is that correct? That's an error because I don't know how it can go from 32 back to 30. So that needs to be changed to a 32. All right, that's a mistake on there. And it's pretty straightforward. Hopefully, it doesn't take much to figure out what the volume is. Simple subtraction. I'll take care of the first one. 16.59 minus 0. That's 16.59. Again, notice I don't put units in the table. I only put the units in the heading. We don't want a table to be cluttered up with a bunch of milliliters. Does somebody have the value for the second one? Again, I'll take it when you got it. Don't be shy. You got it, Michaela? You just subtract, you bet. 15.66. And the last one, Shauna? 15.75. 15.75. Now, I don't normally make you write down what the color of the phenolphthalein looks like, but I'm just trying to impress on you that if it's really dark, then you've likely gone over. And in this case, you can see that we've gone over maybe by 3/4 of a milliliter, maybe a little more. Now, you might think that that's not much, 3/4 of a milliliter, but when it comes to a titration, that's really unacceptable. If we can get the color change to change in 1 drop or even a half a drop, then we should be able to get to within not a half of a milliliter, but like half of a tenth of a milliliter, 0.05 of a milliliter. So really, this first trial is really quite unacceptable in that we're not going to, use the data. Not that I'm going to say, that's unacceptable, and browbeat you, that type of thing. What were you thinking? That would be funny. But no, I wouldn't be quite that mean. And really, it's truly numerically unacceptable, right? We don't want to use that because that's going to give us an incorrect concentration. So when you actually do your titration, the first one that you run typically goes way over because you're not sure when, and then, and it's super purple, whatever you want to call it, pink, magenta, fuchsia, I don't know, choose whichever word you want to use. And then you use that number to say, all right, when I get down to about 14, I'm going to really slow this down because I obviously overshot that, and then you go drop by drop, and then you get to a good color. There should have actually been a fourth titration done because we typically want 3 good pieces of data so that we can average that and we can go from there. All right? When I was in high school, I was terrible at this because as you saw when I was doing it yesterday, it takes some patience when you get to the end. And this might be a surprise to you, but I'm not a very patient person. I know you probably haven't figured that out yet, but yeah, it's true. And so, yeah, and so I would get frustrated at the end and just, good enough. Now, actually, my high school teacher, when we did this lab, and it was grade 11, marked part of our report, like a significant chunk, like half of it, was on how close you were to the proper concentration. So he would take an average of all of the students' numbers, and if there were some outliers, they were obviously not good. And then he did the titration himself, and he did this average. And then depending on how far you were from the average, you were docked marks. Oh, yeah. Yeah, it was mean. My partner had to go to some conference. It was one of these leadership conferences thing. He went away to Ottawa, and I said, don't worry about it. I'll get the data for you. I'll get it. Don't worry. No problem. I think we got a 4 out of 10 on that chunk. Yeah. Yeah, so don't worry. I won't be marking you on how close you are to the number. But it would be nice to have an effort on getting it to a nice light pink. But I won't be that mean. Okay, let's take these numbers and complete the problem here. So I'm going to, I'm out of space. That's interesting. Never thought of that. Can't do it on the board. See if I can add a slide here. Sometimes I can add a blank slide. There it is. Let's try adding a blank slide. There we go. That'll work. Okay, so we're going to finish this one off. First, we want to get the average volume of the NaOH, right? Average volume of NaOH. And we're only going to use the last two numbers because the first one was really not a good, titration. So what were the last two numbers? We had, I believe, a 15.66 plus 15 point, I think a 7.5? Yep. 7.5, right? We add them up, and here we're going to divide it by 2, and I'll take that average when you've got it. To 2 decimals, please. So we're going to round to the second decimal. Yep. 15.71. 15.71 milliliters. And now we solve the problem just like we did before. All right. Now we've got the number to put underneath the sodium hydroxide, and we continue. And I can't even remember if it was sodium hydroxide. I'm just assuming it was. Sodium hydroxide plus, and I can't go back, because if I go back, I lose my writing. Oh, it's potassium hydroxide. Rats. All right, let me fix. All right, where's my eraser? Eraser. We'll go with little eraser. See if I can get rid of that. We'll get rid of this. Okay. What was that? K. And what's the acid? Is it hydrochloric? Hydrochloric. HCl. Oh, and you know what? This is the acid, isn't it? Those are the acid numbers. Read the question. Those are the acid numbers, aren't they? Really messing you guys up. It's exciting. Going to put that out on the internet. Good. So these are the acid numbers. This is the HCl. Yeah, sorry. I was busy finding the blank page thing. That's what screwed me up. So this is our 15.71 milliliters, which means I know the concentration of the HCl this time. I'm looking for the concentration of the base. I got it backwards. In this case, the acid was in the burette, and the base was in the Erlenmeyer flask. So what was the concentration of the acid? Did it say? I hope it did. Yep. 0.5402 moles per liter. 10 milliliters was the other sample. Again, I'm not sure anymore, and I don't want to flip back to the slide. Was it in 10 milliliters of the KOH? 10 milliliters. And again, C equals N over V. Moles, mole ratio, moles. So this time we'll come around this way. And to complete it, right, to balance it, it's 1-to-1, 1H to 1OH. That gets us a KCl, so it's a 1-to-1. Again, C equals N over V, and then I go get my information. 0.01571 liters, 0.5402 moles per liter, and again 1-to-1. This time we do have 4 significant digits in our concentration, so we'll keep 4 significant digits. Again, I'll take that number when you got it. Yep. 8.487 times 10 to the negative 3 moles, making good use of the scientific notation feature on our calculator. Nice job. And now we'll put it in there. 8.487 times 10 to the negative 3 moles. over 0.01000 liters. And again, it's going to be like multiplying by 100, and you're going to get an answer of 0.8487 moles per liter. 4 significant digits on that one. Okay? All right? So that's how you do a titration calculation. It's not that tough. It's, like I said, just like any stoichiometry problem, except we're always dealing with acids and bases. Now, one heads up, there is a question or a couple of them on this sheet where instead of starting with a solution, you're starting with a solid, right? You've got a certain mass of a substance. And don't worry about that because you'll just use its molar mass to get moles and then get the moles on the other side. Because you can titrate against a solid. In actual fact, our first titration that we do next week is going to be using a solid acid, an acid that exists as a solid. We're going to weigh it, then we're going to dissolve it, then we're going to titrate it. And you'll start with a mass. Just use the molar mass, like we would any stoichiometry to get the moles. All right?
Mr. Sanders?
Yep.
Could Christine Hoven come to the main office for just a moment?
Yep.